Okay, hello everyone. Let's start this lecture. So this lecture would be the continuation of the previous lecture. So let's start by saying what we did in the previous lecture. In the previous lecture, we assumed we have an open-ended waveguide antenna. So this is essentially the open-ended waveguide that antenna that assume we have. I mean, if I want to show it to you, this is the input port of the open-ended waveguide to feed it with the coaxial cable. So that's what we had, and then we said we know the electric field over the aperture. In fact, this is from my previous lecture. It's a half cosine in the fundamental mode, which we explained. It is TE10. Then we said if we want to know far field, we need to know the electric field over the whole XY plane. So to handle that, we assume that let's assume this waveguide its aperture is mounted on a PEC plane. So this is essentially a copper tape that I have. So the aperture of the waveguide is mounted on a PEC plane. So this is going to be our XY plane. Over the aperture, we know the field, and we know that E tangential over the metal is 0. In fact, we know the field everywhere on the XY plane now. So we assume that this is very big, so we can say it goes to infinity. Then we said then we obtained our f, which was the 2D Fourier transform of the electric field on the xy plane. We obtained that, and then we said E and H in the far field would be equal to this. So remember, I want to emphasize that again, that in this type of antenna, aperture antenna, you would be given an E over the aperture. T means tangential, as we explained before. Then you find this auxiliary function, which we discussed, that's 2D Fourier transform f. And then from this f, you go to E and H in the far field. So we had this, and then from here, we went to this, and then we found our E and H in the far field. Then we did something at the very end of the previous lecture. We said, can we simplify this E and H expression based on knowing that we are interested only in E plane? So then we explained that E plane for this antenna is the YZ plane. So if this is the antenna, the E plane would be this plane. So that would be, so if I get a plane, this would be my E plane essentially. So if that's the antenna, this gives the three-dimensional pattern. But if you want one cut, you need to be on the YZ plane. So that's my cut. So this would be the E plane of the antenna. And then I said if you want to obtain E plane, then you need to know what is YZ in the spherical coordinate. Then we discussed that's phi equal 90 brings you to y axis. So that's going to make it YZ plane. Now, similarly, I want to start today's lecture by completing what was left from previous lecture, and that's H plane. Now, similarly, H plane contains the direction of maximum radiation, which is Z, and also the direction of magnetic field. So if this is my E, in the far field, naturally magnetic field would be like that, and this is the direction of radiation. So H plane, so if this is E plane, then this would be H plane. So for this antenna, this is E plane, and this would be my H plane. So H plane would be XZ plane. So I can write it here that H plane would be XZ plane. And if you want to be in a spherical coordinate, you want to be on X. So you say, I'm going to be phi at phi equal 0. So that would be your H plane. So if I do that, then what's going to happen to my F here? So if phi is equal 0, what's going to happen? So your E becomes, you see, if phi becomes 0, this term would be gone, and you only have this term. So you're going to get your EJK, e to the power of minus JKR, divided by 2 pi r, and then you're going to have a phi hat component cos theta F Y. So that becomes your electric field on the E plane. So again, I'm repeating myself, but I think that's important. If this is your, this is our H plane. So okay, so this is our electric field on the H plane. The other observation that you can have is that because this is over the H plane, and this is in fact your H plane. Something that you need to be careful and you should check to see if your calculation is correct or not is that if you are on this H plane, which is this, you could actually, if you set theta equal 90 as well, so already phi is equal 0, so you are on the H plane. But if you set theta equal 90, remember theta equal 90 brings you to the XY plane anyways. So when you are on the H plane, if you set theta equal 90, you're coming to the XY plane. And then you notice here that phi hat is always tangential to XY plane. So remember, if this is XY, phi hat is like this. These are your phi hat. So if you look at your phi hat, it's always tangential. So you ask yourself, if I evaluate this electric field on the XY plane in the H plane, then I'm going to have a phi hat component. But I know that tangential electric field over the PEC needs to be 0 because remember, this is mounted on a PEC. So we want to check that that's going to be the case or not. And we immediately see that's the case because if you are on the H plane, this is your expression. And if you further on, you say, I want to check what's happening very far on the x-axis. Then you are on the PEC, you have a phi hat component. It's tangential to the XY plane. So, but then immediately you see that if you are on the XY plane, then theta is 90. So its cos of 90, it's 0. So the tangential component vanishes. So that also confirms that that's correct. This is a bit of detail, but I think it's still good to check these type of things after calculation. Probably the more important thing is the same thing that I mentioned in the previous lecture, that you immediately see that your far field pattern depends on the Fourier transform, because this was the Fourier transform of the aperture field, and now you immediately see that they are completely related. So this was E on the H plane, and in the previous lecture I also wrote E in the E plane. So E in the E plane is for phi equal 90, and if I substitute phi equal 90, I'll get this. This goes to 0 because cos of 90 is 0. So in the E plane, this was my E plane, then it's directly related to the Fourier transform. In the H plane, I have this factor cos of t as well here. But you see the importance of Fourier transform. So that's something that now we know the E plane and H plane. But now if you want to even be more accurate and start calculating this more accurately, not more accurately, more specifically, then perhaps you can start substituting for A and B in the equations. And I guess in the previous lecture, I wrote the dimension, or maybe 2 lectures ago, I wrote the dimension of different waveguide. For example, WR90 waveguide, which is for X band, A is 22.86 millimeter, and B is 10.16 millimeter. So that's your B, that's your A. And so you can start substituting them, and you're going to have substitution for A and B, and you can calculate this. The other way that you can just understand approximately, and at the center frequency, for example, for this one, 10 gigahertz is approximately the center frequency. So if we go by 10 gigahertz, for example, 10 gigahertz, the wavelength is 3 centimeter or 30 millimeter. So A at the center frequency is about 2 lambda divided by 3. Now, if I check it with that, 2 lambda divided by 3 for this case would be, sorry, 30 millimeter, would be about 20 millimeter. Here is 22.83. And B is, you can approximate that the center frequency approximately by lambda by 3. I mean, there is no reason to approximate it, but it gives you an idea before about the size of the antenna. So if I go 30 divided by 3, it gives you 10. I'm at 10.16. So that makes sense. So if I go by this type of approximation, I can also simplify that. And the reason is, for example, look at this one. Ky is k, which is 2 pi lambda, sine theta sine phi, and then b, I can maybe write it as lambda divided by 3, and then I have 1 divided by 2 here. So lambda and lambda cancel, so you can take advantage of this cancellation, and then 2 and 2 cancel here, so you end up with pi divided by 3 sine theta sine phi here, and you can do the same thing for this item here as well. So you can keep going and calculate the pattern of the antenna. Something now I want to mention here is that, remember, if you have this PEC plane here and your open-ended waveguide antenna is mounted here, then if this PEC plane is infinite size, there would be no back radiation. So it's going to have complete shielding. Of course, if you don't have it, or if the size is small, then you're going to have back radiation. And in fact, in the videos related to Lab 3, we perform experiment. This is from LabVolt system, the training system that we are using. We actually measure the radiation pattern of this in E plane and H plane. So you can check, I think it's Lab 3, part 1. So then you clearly see that this one has back radiation, because in the measurement, we're not going to use that. It's going to be on its own. Now that we discuss the fact that discuss this situation, I think it's good to start another discussion, and that discussion relies on this situation, that what happens if we don't have that PEC around the antenna. So if I have this, so this was what I studied. I assume that I have PEC here, perfect electric conductor or metal, and then I have the aperture of my open-ended waveguide. And this is PEC. So the nice thing about that, I know E tangential over PEC is 0. So therefore I know the field everywhere. Now, my question is, what's going to happen if we just have the open-ended waveguide antenna and we don't have anything? So that means we would like to operate it just like that, without mounting it on the PEC. So when it comes to this calculation, one thing you could do is to assume that the field here is essentially the same as before, and then you assume the field everywhere else is 0, exactly like that. Of course, that gives you a little bit of error, but in situations, this could be acceptable. But of course, that's not going to be exactly as that, because we won't know the field exactly. The nice thing about PEC plane is that we know the field exactly. But that's one way of thinking about that, to just assume that you have the cosine taper electric field here, and outside that, on this plane is, and the XY plane, the remaining field is 0. So I have a couple of things, and I'm going to share it with you to see what kind of errors you're going to be getting for making this assumption that even though you don't have PEC, you can assume here is 0, and you just have the cosine taper here. So let's check what sort of approximation we're gonna have. Okay, to understand the effect of this approximation, let's write the E-plane pattern of this antenna that we studied. We already did that in the previous lecture, but let's write it again, and let's see what would be its E-plane cut. So what I'm going to do, because if we know electric field, we know magnetic field. So I'm going to remove magnetic field from here. So we don't need magnetic field so that I can use this space here. So remember, this was X, this was Y. So E plane was YZ, and YZ is phi equal 90. That's what we stated in the previous lecture. Now, if I go with YZ plane, so I'm only considering E plane, then my E, forget about this part because this is just a constant for a constant R, would be proportional to, so phi 90, this term vanishes, this term becomes 1. I'm going to have just Fy. Now, this is my Fy, of course, but I can still do more simplification. The reason is, what is your Kx? Is K sine theta cos phi. Now, phi is 90, so Kx goes to 0. If Kx goes to 0, this goes to 1. Cos of 0 is 1, so I'm going to have a simplification here. And this is also Kx is 0, so this is going to be 0. So I'm going to have a constant term times this sinc function. So this would be constant, this would be 1. So I'm just going to rely on this. So I'm going to say this is going to also be proportional to sinc of Ky. And remember, Ky is K sine theta sine phi. But because phi is 90, this becomes K sine theta. So this becomes Kb sine theta divided by 2. So this tells me that my E in the E plane cut is going to be proportional with this angular dependency. The rest of the term were constant. So, and this is for this, which everything is perfect. I have a cosine taper here. I know my tangential field over PEC is 0, and everything is beautiful in this case. But now, what would be the situation for this antenna in the E plane? So if you calculate that more rigorously compared to just assuming things are 0, then this is the result that you're going to get. And I'm going to give the citation in the caption so that you can check more details. So then you're going to have this. So E plane would be this sinc function that we have, which is Kb sine theta divided by 2. But then you're going to have one extra factor. And the extra factor that you have is going to be multiplied by 1 plus cos theta divided by 2. So you're going to get this, but then you're going to also have an extra factor because you didn't have this perfect PEC for this case. Now, so if you go by this method for that, that means assuming everything is 0, then the error term that you have is essentially this. Now let's check this error term and understand its effect. So this error term is essentially the error vanishes if you choose theta to be theta equals 0, because if theta is equal 0, cos of 0 is 1, 1 plus 1, 2, 2 divided by 2, 1. So this becomes 1, this becomes identical to this situation. Now, what is theta equals 0? Look at this. This is my z-axis. On the z-axis, theta is equal 0. So this is also my main beam. So this approximation, if you just assume outside is 0 without having PEC, is a good approximation when you are right on the main beam, because essentially this becomes 1 plus 1 divided by 2. And then as you diverge from your main beam, this becomes more different compared to this one. So if you do that, and if you make this assumption, and you calculate it, and if I give you an open-ended waveguide antenna, I'm assuming that I accept it from you if you assume outside is 0 in this course, then you should also know that this way that you are doing has an approximation involved, and this approximation is more accurate when you are on the main beam. When you are diverging from the main beam, you get more the effect of this term here. So that's one thing to keep in mind, and this was for the E plane. Now let's study the same thing for the H plane. Now, if I go by H-plane, let's see what is this situation. So the E-plane, so the E field on the H-plane. So by the way, I'd like to keep saying this, although probably by now you already know. You see, H-plane is a geometrical plane. Sometimes some people think that when they have H plane, they always need to write this is the magnetic field because it says H. But H plane is just a geometrical plane. You can write what is electric field on the H plane, or you can write what is magnetic field on the H plane. But most of the time we write electric field because in the far field, electric field and magnetic field are related, as you know. So don't think that if it's H plane, you have to write magnetic field. It's just a geometrical plane. We named it H plane. Now, E on the H plane is going to be proportional to, first of all, let me also write H plane, as we discussed in this lecture, is XZ plane, and XZ plane is phi equals 0. So, and if phi is equals 0, this term vanishes. We come to this term, and this term becomes cos theta Fy, and because phi is equals 0, cos of 0, 1. So I'm going to have that, cos theta Fy. Now I'm going to substitute for Kx and Ky. Now, what would be my Kx and Ky? My Kx is K sine theta cos phi. Phi is 0, therefore this becomes K sine theta. My Ky becomes K sine theta sine phi. Phi is 0, this becomes 0. If Ky becomes 0, I'm having sinc of 0, but sinc of 0 is 1. Remember sinc function? This is 0, and then this is 1. So for 0, it's 1. So sinc is 1. And you can also understand it by writing sinc of x as sine of x, x. If x goes to 0, you know that sine of x divided by x is essentially 1. The reason is this is your sine, and if x is a small, this portion of sine is very similar to y equal x line. So this is y equals sine x. So when x is a small, which is here, then these two are very similar to each other. Therefore, sinc of 0 is 1. So that becomes 1. Therefore, I'm going to get proportional to cos theta, that, and then another angular dependency that I have is here, 1 pi squared minus kx was k sine theta, so ka sine theta to the power of 2, and then this was 1, then I get this, which is cos ka sine theta divided by 2, so cos ka sine theta divided by 2. So this is going to be the H plane, electric field in the H plane of the antenna, which is ideal. It has mounted on a PEC. So you have an aperture mounted on a PEC plane. But now if you go with this aperture that there is no PEC plane, but you are assuming 0 outside, then what would be the difference between this and that? The main difference here is that this cos of theta that you have needs to be replaced by 1 plus cos theta divided by 2. So essentially, you need to replace that by 1 plus cos theta divided by 2. So if you, when you are solving for this problem, when there is no PEC plane, then you are just assuming that there is a PEC plane without really a PEC plane being there, you get this answer. But the correct answer would be if you had 1 plus cos theta divided by 2. So again, as you see, if theta is 0, this term is cos of 0, 1. This term is 1 plus cos of 0, 1 plus 1 divided by 2, again 1. So these two terms are not much different if you are on theta equals 0, which is the direction of maximum radiation, your main beam. As you change your theta from your z-axis, as you diverge from your z-axis, as you get away from your z-axis, you're gonna see the difference between these two components. So in summary, if we don't have that, so if this is my antenna, so originally I started my discussion by this, that we have something here and this PEC plane is big. But if we don't have this, we can still assume that the situation is like that, but of course we get some error because of this assumption. And the error is less when it comes to closer to the main beam but then as you diverge from main beam, the error would be more. And also remember, this always have back radiation. So it's gonna have some back radiation. But if you have a PEC plane which is infinite in size, of course it's just gonna be in the forward hemisphere, and backward hemisphere you will have no radiation. Okay, so far we've covered E-plane and H-plane of an open-ended waveguide antenna, and in general, the arbitrary aperture with the size of A and B. So to just review that, we had essentially a PEC plane, and here we had an aperture of the size A and B, and here we had some electric field distribution. That was our aperture antenna. And if the size of A and B is in such a way that it relates to an open-ended waveguide antenna, then you would have essentially an open-ended waveguide antenna mounted on a PEC plane. So this was our PEC plane. Now, I'd like to have like a specific case in which these A and B are certain sizes. If they are certain sizes, as we saw, that relates to an open-ended waveguide antenna. But we have another type of aperture that's called a slot antenna. And in this configuration, this is again our flat metallic plane that we had, PEC, and then this is essentially the aperture that we have. And this size, this A, is about lambda by 2, and this B, or width, is much smaller than lambda. So this is a particular case that we call a slot antenna. This is an aperture antenna, but because of these specific sizes, we're gonna have we can actually use the equations that we already found to calculate E-plane and H-plane for this. And again, we're gonna have our electric field like that. Of course, it has to go to 0 because that's a metal at the site. So this is gonna be our slot antenna. So now, before going into a mathematical equation, let's consider a structure which is related to a slot antenna. To understand it better, perhaps it's good that I say how we can excite this slot antenna. In the case of open-ended waveguide antenna, you remember we had a waveguide in the back. So essentially we had a waveguide and we excite this waveguide, and then this is the way that we're gonna get our electric field. In the case of just the slot in the metallic plane, perhaps you can use a 2-wire transmission line like this to bring the power to the slot, and then it can radiate for you. Or the other way you can do that perhaps is to use a coaxial cable. So this could be, for example, your coaxial cable. One side is connected here, and then the inner conductor is soldered here. So something like that, or maybe with 2-wire transmission line, it's easier to see. So I'm just gonna redraw the 2-wire transmission line. So this is the situation that we have for this. Now, if you consider this, remember this is PEC, but for a second, just forget about PEC completely and consider this situation, that you only have this. So assume that you only have this part. So you're gonna have metal here, metal here, metal here, metal here, metal here, metal here. So this is actually very interesting because this is going to be transmission line. Remember, this size here, by definition of a slot antenna, B is much smaller than wavelengths. And you know, if you have two conductors with the separation much smaller than wavelengths, then you can think of them as transmission line. So if I think of this as transmission line, and for example, if I consider this part lambda by 4, this part lambda by 4, then I can think of current distribution perhaps like this. And so remember, opposite direction and like this. So this is going to be the current distribution on the line. I'm going to give a caption so that you see the more details in a different book. So as you see here, again, these guys are canceling each other. So so these currents are canceling each other, and then you only get this current and this current that are in phase. So you may get radiation from them, but there's going to be very small. So it's not going to be an efficient radiator because this is by definition is so tiny, is much smaller than wavelength. So it's not going to be a good radiator. But then what happens here, this is not a good radiator, but then as soon as you put this PEC here, it's going to be an interesting radiator because now these currents are not just limited to this small piece of wire. You essentially have the whole PEC so that you may get currents from this structure. So you see now the currents are not just limited to this, they can flow on the PEC, and that makes this an efficient antenna. So that's our a slot antenna. And something that's also interesting in this antenna in terms of its application, remember in the case of patch antenna, we thought of it as two radiating slots, although there was no PEC plane and a cut through PEC. But look at this structure. This width was delta L, which was much smaller than lambda. This was the fringing effect. So as you see, if you now think of this as your aperture, also this you can think of this as radiating slots because this is a small with respect to wavelength. So this is something to keep in mind when you are looking at that. So now when you are considering this structure, let me bring an example of this so that you can actually see one example of these slots. Okay, so if you remember, this was our open-ended waveguide antenna. So we had a relatively, reasonable size aperture. We cannot call it big aperture, but it's a reasonable size aperture. If you remember, the width was about lambda by 3 at the center frequency. But now this is one type of a slot antenna. So, and as you see, we have a few of them here. I don't know how good you can see that, but if you can see that, then you see one here, one here, one here, one here, one here, one here. In total, we have 6 of them. And if you pay attention here, you see that the widths are so small. When you compare it, for example, with the widths of the open-ended waveguide antenna. So you see that the widths are so small compared to that. So that's one thing that distinguishes this from an open-ended waveguide antenna. So another thing that it's good to be mentioned here is about feeding of this. So something that I want to remind you about, and that was related to a patch antenna. You remember if I show a patch antenna from the side, so this was metallic ground, this was my substrate, this was the patch, and we wanted to feed this. We said here the impedance is going to be very large. Here at the center, the impedance is going to be very small. So we probably feed it with some offset. For example, you remember we're going to feed it at this point. So we had some offset here. So this is very similar to this case. So in fact, If you feed it at the center, you're going to have a big impedance mismatch between 50 ohm, which is your line, and the impedance that you're going to see at this point. So that's why we don't feed it there. And if we go here, then the impedance would be very small. So that's if you compare it, is exactly opposite. Here at the center, it's very high. For the patch, it was very small, and at the side, it becomes very small. At the patch, becomes very high. And maybe based on transmission line theory, you can connect it to the fact that here you have your short circuit. At the patch, you have, at this point, you have open circuit. These two are not connected. So I mean, you may think of it this way. So now that we know this, when we want to fit this structure, it's quite usually, I mean, it's usually good to, as we mentioned, if this is the center, we feed it off-centered, and this is a distance typically a lambda by 20 separated from the side. Then you feed it from here, and this is 50 ohm, and you may hopefully get a good match for this separation. So similar to patch, you don't feed it right at the center. You need to have some off-centered, for example, in this case lambda by 20. The other thing with this type of antenna is that if you have some field distribution here, so let's say this is your field distribution here, and this is just a plane, metallic plane, and you have a slot in the metallic plane. So of course, it can radiate toward you, and it can also radiate backward. So if you don't want to have radiation in the back, then maybe you can have a box, metallic box in the back. So if you have a metallic box in the back, that essentially means you have a structure like this, so that this is completely metallic. So that when the wave goes in the back, it's going to reflect back, because this is metal, of course. So this is metal, and then continue in the forward direction. So essentially, you create something in the back so that the backward waves, sorry, the wave that goes in the backward direction, then they're going to be reflected, and then you get your radiation in the half a space toward yourself. So, and to do that, this is usually chosen to be this length of this box is chosen to be usually lambda by 4. And to understand this lambda by 4 intuitively, if the wave goes lambda by 4, reflect back and come back, then the wave has traveled lambda by 4 plus lambda by 4, which is lambda by 2. And we know that half a wavelength is 180-degree phase shift. You can understand it by this, e to the power of minus jkd. So, and d is the distance, so k is 2 pi lambda, d is lambda by 2, you get pi. So you get 180-degree phase shift. So that means if this is the direction of electric field, 180-degree phase shift, that means now it's on the opposite direction. But remember, the reason for reflection is to have a metallic plane here too. So it goes there and then come back here. So this metallic plane, if, for example, imagine the whiteboard is metal, if this is the electric field incident on the metal, you need the E tangential on the metal needs to be 0. So you're going to be creating an electric field with 180-degree phase shift to cancel the effect of this. So that means metal is going to create for you another 180-degree phase shift. And you already have 180 from the distance, 180 for the boundary condition of metal, you get 360. So that's why this lambda divided by 4 is a good distance when you are creating this box. So this is called boxed in a slot antenna, so that you can get your forward direction radiation. So this is something to keep in mind. But now, if we continue our focus on this, this is very closely related to dipole antenna, in fact. So If we consider this antenna here and change the PEC to air and change this air in the slot to PEC, what's going to happen is that we're going to essentially have, so imagine this is your excitation somewhere here. It could be off-centered, but right now I'm assuming centered in this case. So I'm changing this to 2 PEC strip, and then I'm removing PEC and changing with air. So this is essentially, this structure will be called complementary to this structure because you're changing PEC here and have air and air here to PEC. Now, you can easily see that the radiation pattern of these two are very much related, and I'm going to show it to you when I'm discussing the radiation pattern of this. And also you can understand that their input impedance is related. These are all enabled by Babine principle, which is, and its extension by Booker. So the input impedance of these two structures, let's call this, for example, your antenna, and this is the complementary form of this antenna. It's going to be eta divided by 2, eta to the power of 2 divided by 4. Now, if you have a half a wavelength, because we assume this is half a wavelength, center-fed dipole antenna, its input impedance is about 73 plus J 42.5. I mean, you remember that you need to make it a slightly less than half a wavelength to remove this reactive part. And then equal eta is 377 to the power of 4. And then you can find the Z of, maybe I call it S to represent a slot antenna. And then you can find Z of a slot antenna. And I hopefully have the calculation for this. That's an example from our textbook by Professor Balonis and Wiley as the publisher. So here I'm going to get for ZS from this equation 362.95 minus J211.31. So that would be the input impedance of this slot antenna, assuming that you are fitting it at the center. And even if you just look at the real part of this, it's not appropriate to be matched to 50 ohm. If you are about 73, it's reasonable. But when you get to that, that means you are very high in terms of impedance. That's exactly what we predicted. We said here you should have a high impedance value. You will have that. So that's why you make it a little bit offset. So this actually shows you that that's not a good location to feed the slot antenna. Okay, now that we've seen that, the next step would be to go to a little bit of mathematics and figure out this radiation pattern of this structure. Okay, let's start finding the radiation pattern of the slot antenna. So for this, let me just clean up this figure here. So you have a slot, and this is your A, this is your B. And remember, the main thing here is that this B is much smaller than wavelengths. So B much smaller than wavelengths. Now we've already saw E plane and H plane for an arbitrary A and B in this lecture. So I have them here. So I'm just going to write them. So remember, we had our E as R, theta, and phi in the E plane to be equal to theta hat JKAB, or K naught if you desire, E naught divided by pi square e to the power of minus JKR, . We had a sinc function KB sine theta divided by 2. And we had another E, this time for H plane, which was phi hat JK AB E naught pi square minus KA sine theta square e to the power of minus JKRR cos KA sine theta divided by 2 cos theta. So remember, we had these under the assumption that this PEC plane is very large. And we discussed that if there is no PEC plane, this will change. But here we are assuming that this PEC plane is also very large. So that would be our assumption here as well. Okay, so these were for general A and B. So now how can we make it specific to this? We need to take into account that our B, it becomes much smaller than wavelengths. Now, B is right here in this case. So let's see how we can compare B with the wavelengths there. So if I consider B becomes much smaller than wavelengths, let's see what I'm going to have. If B becomes much smaller than wavelengths, then what would be my sink? Sink of K becomes 2 pi lambda B sine theta divided by 2. But now my B divided by lambda becomes extremely small. And look at the sink function. So this is sink function. So you see, if I have a very small value, for example here, the value of sink is about 1. So, and if B divided by lambda goes to 0, becomes very small, sink value is about 1. So what I'll do is that I'll say, and to just emphasize that, remember, sink of 0 is 1. If I want to be more mathematical, remember, sink is sine of x divided by x. If x goes to 0, this is 1. So anyways, if that's the case, I know that if B is much smaller than lambda, therefore E in E plane becomes theta hat JK AB E naught pi square e to the power of minus JKRR times 1. So that becomes essentially my E plane. And this is amazing because this is actually shows something interesting. And that, if you look at that, this is essentially a constant number with respect to angular distribution. If you change the angle, nothing changes. So by the way, let's have our axis here, x, y, and z toward u. And we know that E plane, because this is the direction of electric field, like this. E plane is YZ plane. So if I plot YZ plane, so if this is my Z and this is my Y, and if this is my Y, this is essentially the dimension of the slot. You see, this is just this small b that I have. Now, if you look at the radiation pattern, is essentially omnidirectional. Look at this, because it doesn't depend on the distance. So essentially, it radiates everywhere exactly the same. And remember that the direction of electric field is theta hat. So when the direction of electric field is theta hat, at this location, this is going to be perpendicular, because this is PEC. This is going to be perpendicular to the PEC, which is fine, because electric field over the PEC can only be normal to the PEC, cannot be tangential to the PEC. Tangential field to the PEC is 0. So you look at this, you see that on E plane, you are essentially have this structure. Now, remember this Babine principle and the extension by Booker that we said this is the complementary antenna to this dipole antenna. Now, if you go to dipole antenna, You know that for dipole antenna, H plane is like this. This is now E plane. You see, E plane of this has this omnidirectional characteristic, but the H plane of dipole had this omnidirectional characteristic. So that somehow shows their relation, but there are differences too. This happens in the E plane of this, but for dipole, it happened in the H plane, and also polarization was different. So the polarization of this right now is vertical. If you look at that, this is the way that it radiates. If you have your complementary dipole, would be the dipole would be in this direction, and the electric field becomes horizontal. So the polarization also changes. So when you have the complementary structure, you need to be aware of these things. So now let's go and check the H plane. Okay, now let's focus on the H plane of this slot antenna. So for the E plane, we took advantage of the fact that B with respect to lambda, which is inside K, becomes small. So we approximated sync with 1, and therefore we got an omnidirectional pattern, no angular dependency here. But now for the H plane, we say that A is approximately half a wavelength. So I'm just going to substitute A half a wavelength here. So therefore, this is going to be E in the H plane is going to be equal to phi hat JKAB E naught. And then this is going to be 2 pi lambda divided by 2 sine theta. This cancel, you get pi sine theta. So pi square minus pi square sine square theta for this. And then you get e to the power of minus jkrr. And then here you're going to have again 2 pi lambda by 2. That's going to give you pi. Then you have a 2. That's going to give you cos pi 2 sine theta. And then you have a cos theta here. So that's going to be your cos theta. But remember, here you have pi square 1 minus sine 2. So you can write that as pi square cos square theta. And then you can have this cos square and cos cancel. And then you're going to have phi hat jk AB E naught e to the power of minus jkr r cos pi 2 sine theta divided by cos theta. So this is essentially a constant with no dependency on the angles, and this is essentially governs your radiation pattern. And if you plot that, you're going to see that, first of all, you are in H plane. So this is going to be your X, this is going to be your Z. So you're going to see that exactly you get your donut shape that you used to see for the E plane of the dipole antenna. But here now you see that in the H plane of this antenna. So this is like that, and you can also understand it by checking the half wavelength dipole in the textbook in terms of its radiation pattern. If you look at the half a wavelength dipole in the textbook, you're gonna see something like this. You're gonna see a dipole, and in the textbook, dipole is along Z when they study half a wavelength dipole. And let's assume this is half a wavelength. And look at its pattern. The pattern in the E plane, remember this is H plane, but for dipole would be E plane. The E plane would be cos pi 2 sine theta. Sorry, in the textbook would be cos pi 2 cos theta divided by sine theta. That would be the pattern for a half a wavelength dipole along Z. Let me check that. It's cos pi 2 cos theta divided by sine. Yes, this is going to be the pattern for this, and you get your donut shape like that. But if you look at that, there are a couple of changes here. This is sine theta, this is cos theta. this is cos theta, this is sine theta. And you might say, okay, Puyan, this is not exactly that, but remember, you're missing something. This expression for the dipole along Z, but the complementary structure to this is a dipole along X. So this is a dipole along Z like that. This is a dipole along X. So essentially for this dipole antenna, the axis is along X. But for this dipole antenna that we have the expression, the axis is along Z. So theta equals 0 in this case, theta equals 0 in this case, which is along Z axis, is not going to be the same for this, because now along the axis is actually X axis, which is theta equal 90. Remember, this is Z, so you go theta 90, you get to X axis. So you see there you have a 90-degree phase shift between your axis here. So if you apply that 90-degree, your sine becomes cos and your cos become sine, and therefore they're actually the same thing. So the point here is that you see how closely this relates to the dipole antenna. And if in the exam I mentioned about a slot antenna, you essentially want to make sure that when you are doing your calculation, you can simplify this sink to be equal to 1, because if you make that sink equal to 1, then everything in terms of calculation becomes much easier. So you get your donut shape, and then you also get your omnidirectional in a different plane. Okay, so one last addition is that in one of the videos regarding to the measurement, we're gonna use this type of a slot antenna, which is in a waveguide. So we call it a slotted waveguide antenna. We're gonna perform measurements from this one, and then you get to know about this in more details. And this is nice because this is also an array. So it's an array of a slot antenna, but these are fed using a waveguide, as you're gonna see in the video related to this particular lab. Thank you very much.